an interstellar object whirling through our solar system is actually a nuclear-powered spacecraft sent by aliens to test how humans respond.
3. I/Atlas just entered our solar system, and it's not following the rules of gravity.
On the 1st of July, NASA detected a mysterious object speeding toward Earth, and some actual bona fide experts think it might not be your typical space rock or maybe any kind of rock or a natural phenomenon at all.
What began as a fast-moving blip on astronomers' instruments quickly turned into a source of growing concern. Numbers are failing. Predictions are collapsing.
With 0 meaning it's a natural object, like a comet, for sure. And 10 meaning it's definitely a technological object.
And a terrifying question is spreading across the global astronomy community. What is Atlas doing? And why can't anyone explain it?
Supposed comet is catching the attention of some of the nation's most renowned scientists, as one Harvard professor is raising the theory this may actually be a piece of alien technology.
A cosmic intruder too fast to belong. The Atlas survey system, designed to detect hazardous objects near Earth, picked up a fast-moving speck of light that did not match the usual patterns. At first glance, it could have been mistaken for a comet or asteroid, but the numbers coming back from observatories told a far stranger story. Atlas was moving at nearly 60 kilometers per second. For perspective, Earth's escape velocity, the speed needed to leave our planet's gravity, is about 11 kilometers per second. Even the sun's immense pull cannot keep hold of something moving that fast. This speed alone confirmed that Atlas was not native to our solar system. It was an interstellar object, arriving from deep space.
A Harvard astrophysicist believes there's a strong likelihood this is a craft of alien origin, and the implications, obviously, for humanity would be profound.
It was not a comet from the Oort cloud and not a returning body on a long loop. It was a visitor from the void between the stars. Astronomers quickly designated it 3E/Atlas, the third confirmed interstellar object, after Oumuamua in 2017 and Comet Borisov in 2019. But Atlas was different in ways that demanded attention. Oumuamua was only a few hundred meters long and oddly shaped like a shard. Borisov looked much like a normal comet. Atlas, by contrast, was measured at between 3 and 7 kilometers across, making it the largest interstellar body ever tracked. Its path deepened the unease. Most solar system objects move on ellipses or parabolas that curve under the sun's influence. Atlas's orbit, however, was calculated with an eccentricity greater than 6. This was essentially a straight line, a one-way journey that would take Atlas through the solar system and back out again, never to return. No planet, no star, no familiar gravitational force could stop it. Within hours, major observatories in Hawaii, Chile, Spain, and Australia turned their instruments toward Atlas.
A new telescope built to track fast-moving space objects in Chile has caught a comet from beyond the solar system moving across the sky.
Each confirmed the same conclusion. Atlas was interstellar, it was fast, and it was not staying. For astronomers, the discovery was thrilling and alarming. Interstellar objects offer rare clues about the chemistry and conditions around other stars. But their high speed and brief visits mean scientists only get one shot at study before they vanish forever. Questions arose immediately. Why was Atlas moving faster than Oumuamua or Borisov? Where had it come from? Early reconstructions suggested it originated far beyond the nearest stellar neighborhoods, but its exact birthplace was unclear. The fact that it could enter the solar system without detection until the last moment revealed how limited our monitoring systems still are. As the data flowed in, a deeper unease spread. Atlas was unquestionably interstellar, but its orbit hinted at subtleties astronomers did not yet understand. The numbers were solid, the telescopes were precise, yet something about its movement suggested this object might not fit neatly into the rules of orbital mechanics. The orbit that should not exist. Once Atlas was confirmed as interstellar, astronomers began the next step, plotting its orbit. This process normally involves feeding several known variables into a model. These include the sun's gravity, gravitational pulls from nearby planets, the pressure from sunlight, and sometimes additional forces like gas jets or dust escaping from the object's surface. When done correctly, this model will produce a predicted path that matches the object's actual movement through space. With most comets and asteroids, this method works with high precision. But as more observations of Atlas came in, astronomers noticed something that challenged their expectations. Each observation includes a timestamp and a precise location in the sky. These are compared against the predicted path from the model. The small differences between expected and actual position are called residuals. With a normal object, residuals shrink over time as the model improves. But in Atlas's case, some teams began reporting that these differences did not go away. In fact, some believed they were forming a pattern. This raised serious concern. A persistent pattern of residuals suggests the model is missing something, that the object's real motion is being shaped by a force not yet accounted for. In principle, residuals can be caused by things like unmeasured outgassing, rotating surfaces, or irregular shapes. But residuals across multiple independent telescopes and observatories, all pointing to the same mismatch, are harder to dismiss. Not all scientists agree yet on the cause. Some argue that the apparent pattern could still fall within normal observational error, especially for a fast, distant object. Others worry that there may be an actual systematic drift, a gradual, consistent shift in position that cannot be explained by the current model. If that proves true, it would imply that something beyond standard gravitational and radiation forces is affecting Atlas's trajectory. For astronomers, that's not just a technical glitch. It is a warning sign. Because if the models don't line up with the data, then there is something wrong at the systemic level. The numbers are solid, but the fit is off. And if Atlas is drifting for reasons we don't yet understand, then the next question becomes far more urgent. What kind of object could be so massive, yet still move in a way that no current model can fully explain? Too massive to drift. One of the most basic rules of physics is that it takes more force to move a heavy object than a light one. In space, the same rule applies. When scientists estimated the size of Atlas, which is between 3 and 7 kilometers wide, they quickly realized they were dealing with an object that could weigh billions of tons. That kind of mass should make it extremely stable. Small forces like solar radiation or jets of gas should have only a tiny effect on its motion. This is especially important when studying comets. As a comet nears the sun, heat causes frozen material on its surface to vaporize. This process, called outgassing, releases gas into space and creates visible jets that act like miniature thrusters. These jets can push on the nucleus of the comet and cause its orbit to shift slightly. This effect has been seen in many comets, including 67P, which was studied up close by the European Space Agency's Rosetta mission. In that case, only about 10% of the surface was active, yet it produced a measurable change in motion. With Atlas, scientists did detect signs of outgassing. There was a visible coma, the glowing cloud of gas and dust that surrounds a comet's nucleus. Instruments picked up water vapor and carbon dioxide streaming off the surface. But here is where the concerns begin. Based on the amount of gas being released, the total force generated by the jets should have been small. far too small to move something this massive in any meaningful way. If the reports of Atlas drifting are accurate, and if those changes cannot be explained by outgassing or other known forces, then the scale mismatch becomes a problem. A weak push should not be able to budge a billion-ton object. And yet, that might be what is happening. Some researchers have speculated that either the object is far less dense than originally thought, or that an unknown mechanism is producing more force than expected. Others are not convinced. They argue that the object's mass is still an estimate, and that more data is needed before jumping to conclusions. It's possible that the outgassing is more powerful than initially measured, or that hidden vents beneath the surface are releasing gas unevenly. If that's the case, a revised model could eventually bring the math back into alignment. Still, the fact remains that Atlas sits in a mass range where movement should be minimal. If any orbital changes continue that cannot be explained by standard physics, it would mean something fundamental is missing from current models. The fear is not that physics is broken, but that we may not fully understand how it applies to rare, fast-moving interstellar objects. And the unsettling part? This may not be the first time it has happened. A very different object, seen in 2017, raised a similar alarm. It was smaller, quieter, but its behavior echoed what scientists now think they might be seeing again. The Oumuamua Echo. As Oumuamua passed the Sun, astronomers noticed that it began to accelerate slightly. This change in speed and direction could not be fully explained using gravity alone. Normally, when a comet moves through the inner solar system, it heats up. Sunlight causes the ice on its surface to vaporize. This vapor escapes into space in the form of jets. These jets act like small thrusters, gently pushing the comet and causing it to drift from its predicted path. But Oumuamua did not behave like a normal comet. Telescopes detected no visible coma, which is the bright cloud of gas and dust that forms around a comet when it is active. There were no jets of vapor observed and no dust particles seen around it. In every image, it appeared completely dry and inactive. Despite this, it still moved as if something was applying a small but steady push. To explain the movement, scientists began proposing different theories. One idea was that Oumuamua might have been venting hydrogen gas. In this scenario, the object could have been made of solid hydrogen ice, which would sublimate or turn directly into gas when exposed to heat. Since hydrogen gas is invisible and difficult to detect from Earth, this theory tried to account for the missing evidence of a visible coma. However, there is no direct observation confirming that Oumuamua was made of hydrogen, and some physicists questioned whether such an object could survive the long journey through interstellar space without evaporating. Another theory suggested that Oumuamua might have been extremely thin and lightweight, possibly shaped like a flat sheet. If this were true, sunlight could have pushed against it more effectively than against a typical rock or ice fragment. This would allow radiation pressure, which is the force exerted by photons from the sun, to slowly accelerate the object. This idea was controversial because natural objects with that shape are not known to form in space. Some scientists even speculated that Oumuamua could have been artificial, perhaps a type of light sail or fragment from an unknown technological source. None of these theories were proven. Each one raised as many questions as it tried to answer. The observations remained incomplete, and the data left room for multiple interpretations. In the end, Oumuamua remained a mystery. It was clear that something had pushed it off course, but scientists could not agree on what that something was. Most scientists, while intrigued, eventually treated Oumuamua as an isolated case, a cosmic fluke. It was strange, but in the absence of a second example, it didn't force a change to existing models. The standard thinking was that the next interstellar object would likely behave more like a typical comet. That assumption is now being questioned. With the arrival of 3I/Atlas, astronomers were reminded of Oumuamua's unsolved case. While Atlas and Oumuamua are very different in appearance and scale, the timing and circumstances have raised a disturbing possibility. If even two interstellar objects show behaviors that cannot be fully explained using standard comet physics, the odds of coincidence begin to fall. This isn't just an academic debate. The core concern is that these objects may represent a poorly understood class of interstellar material, one that doesn't behave like any comet or asteroid we've studied before. If interstellar objects do not follow known patterns of motion or composition, then our ability to monitor them or detect them early is seriously limited. And just as the debate over motion reignited, a new mystery appeared not in how Atlas moved, but in what it was made of. The nickel mystery. When astronomers turned their instruments toward Atlas to study its coma, what they found did not make sense. Using high-resolution spectroscopy, researchers identified 22 distinct emission lines for atomic nickel. This was already rare, but what came next was even more shocking. There were no detectable lines for iron. In astrophysics, that kind of result should not happen. Nickel and iron are nearly always found together in space. They are both forged in the final stages of massive stars and released during supernova explosions. These metals are chemically similar and tend to bond with the same materials. Whether in asteroids, meteorites, or comets, they appear side by side in nearly every sample. Finding nickel without iron is not just unusual. It suggests that something is very wrong with our assumptions. There are only a few speculative explanations for this. One is that Atlas formed in a region of space where conditions were so extreme and exotic that iron was somehow filtered out or never included in the first place. Another is that something happened after its formation, which could involve some process that selectively removed or destroyed iron while leaving nickel behind. But scientists have no confirmed mechanisms that can do this on a large scale. If such a process exists, it would represent physics that is completely outside our current models. The chemical confusion deepens with another disturbing discovery. Analysis from the James Webb Space Telescope showed that Atlas was releasing gas in a highly unusual ratio: 8 parts carbon dioxide for every 1 part water vapor. In almost every comet observed in the solar system, this ratio is reversed. Water dominates, and carbon dioxide is a minor component. Atlas flipped that expectation on its head. This gas profile raises serious concerns. Carbon dioxide is a more volatile compound, meaning it turns into gas at lower temperatures than water ice. For a comet to release more carbon dioxide than water at this distance from the Sun suggests that its interior is chemically structured in a way we have never observed before. It does not behave like a typical comet. It does not outgas like one. And now the metal content shows it may not even have been formed like one. Astronomers are now facing the possibility that Atlas may be chemically alien in the most literal sense. Its makeup does not match anything from the Oort cloud, the Kuiper belt, or even interstellar objects previously observed. It moves strangely, and now it appears to be made of materials and proportions that defy current understanding. Some researchers are quietly asking whether Atlas represents a new class of object altogether that was formed in an environment the solar system has never sampled. Others are going further, speculating whether the structure and composition could hint at non-natural origins, though there is no evidence to support that at this time. Regardless of its origin, the implications are the same. If Atlas does not follow the known rules of chemistry or physics, then nothing about it can be predicted with confidence. And if we can't explain what Atlas is made of, how can we possibly prepare for what it might do next? The planetary defense nightmare. Planetary defense depends on our ability to predict how objects move through space. When astronomers track a comet or asteroid, they use mathematical models that calculate where it will go. These models consider the pull of gravity, the pressure from sunlight, and the small pushes caused by gas or dust coming off the object. When the math works, we can forecast a space object's future position with great accuracy. This gives scientists the information they need to plan a response if something ever poses a threat to Earth. But Atlas has raised a serious concern. Some scientists are now questioning whether these models will always work, especially for large objects coming from outside our solar system. If Atlas truly moved in ways that existing models could not fully explain, it creates a gap in the system that keeps Earth safe. Space agencies like NASA are preparing for the possibility of a future impact from a dangerous object. One of the key ideas is called kinetic impact deflection. This means sending a spacecraft to hit the object and change its path. NASA tested this with the DART mission, which successfully shifted the orbit of a small asteroid in 2022. However, that success was based on a simple truth. The asteroid's motion could be predicted. The math was solid, and the results were expected. Even small changes in an object's path can make a huge difference over time. If those changes are not accounted for early, it may appear harmless at first. But later, those same changes could shift it directly into a collision course. And by the time we realize the danger, it might be too late to stop it. This is why Atlas has become a source of deep concern in the planetary defense community. It is not just about this one object. It is about the larger pattern it might represent. If more interstellar objects behave this way, then the methods we rely on to detect and deflect threats might not be enough. Scientists are not saying that Atlas itself is on a collision course with Earth. But the deeper fear is about what comes next. If Atlas exposed weaknesses in our ability to detect and predict large interstellar objects, then we have to ask whether the next one could slip through unnoticed and strike without warning. If we cannot fully explain how these objects move, then we cannot fully protect ourselves. And there is one more possibility that some scientists are just beginning to ask. What if the way some scientists believe Atlas changed course was not just a random result of nature? What if something made it move? Was Atlas actually steered? After all the failed models, chemical surprises, and unexplained motion, a disturbing question has started to take shape. What if Atlas did not simply drift? What if something made it change course? This idea is not based on hard proof. No scientist has confirmed any artificial influence on Atlas. But among astronomers who have studied its motion and chemistry, a few are beginning to ask whether the behavior of Atlas is strange enough to consider alternatives outside natural processes. The main reason for this speculation is the scale and consistency of the unexplained drift. As discussed earlier, Atlas is not a small object. It could be several meters across and billions of kilograms in mass. Natural forces like gas jets or solar radiation are expected to move such objects only slightly. In Atlas's case, the measured shift was larger than expected, and the forces did not fully add up. This gap between the predicted path and the actual motion is what triggered speculation in the first place. One idea, proposed by a few researchers in past cases like Oumuamua, is the concept of light sails. These are extremely thin materials that use sunlight as propulsion. These sails are real technologies that exist in Earth-based research, and under the right conditions, they can steer objects silently through space. If Atlas were hollow or built with a very large surface area, it's possible that it could respond to radiation pressure in unexpected ways. Another idea suggests that Atlas may have internal mechanisms that are unfamiliar to science. Some have asked whether it could be releasing material in a controlled or unusual pattern, not randomly like a natural comet, but in a way that creates precise movement. There is no known natural object that does this deliberately. But the behavior of Atlas raises questions about whether we fully understand how some interstellar bodies operate. The most extreme theory is that Atlas's motion is the result of intelligent design. This would mean that its movement was guided intentionally, either by unknown technology or by some force we cannot detect. The fact that the object's motion cannot yet be fully explained by existing models has left the door open for these conversations to happen. Most scientists are not ready to consider Atlas anything other than a natural interstellar object with highly unusual characteristics. But even the fact that such theories are being discussed reveals how unsettled the field has become. When something defies multiple lines of reasoning, motion, chemistry, and predictability, the scientific community begins to stretch the limits of what they are willing to consider. Atlas may turn out to have a natural explanation. There may be physical forces, material structures, or chemical reactions that we simply do not understand yet. But until those answers are confirmed, we are left with possibilities. Some of them are grounded in new physics, others in ideas that challenge the boundary between nature and intent. What do you think about Atlas's gravity? Comment down below.